This demo is designed to showcase the automated capabilities of the Cognitive Data Modeling module in SEMOSS, which stands for Semantic Open Source Software. Merging databases is a laborious process due to the difficulties in spotting commonalities between the data. By following the 7-step process below, this module can easily identify and verify potential matches between the data. While these routines are useful in automating laborious processes through artificial intelligence and machine learning algorithms, a data steward is still needed to validate the decisions and assist the tool. The first step is to connect to a database to bring in your data. SEMOSS has over 15 external database connectors that allow you to easily import your data into the module. The platform is accessed using this link here. Once you land, you'll notice that there are many different ways to connect to a database. You can either choose to master an existing one, such as the one shown here, or you can connect to an external connector. In this instance, we'll be showing MariaDB. In order to connect to an external connector, you'll need the details for that, such as the hostname and the port. After your data is uploaded, the second step is to see a raw view of your data and to find your columns in the unmastered ontology. On the left-hand side, you'll see the data dictionary. This is a series of tables with logical names and aliases. If we click on a column name, we can see a sample of those values. On the right hand is the schema. These are the physical tables with the hard foreign key relationships. If we zoom out, we can see the unmastered view of the original metamodel. This will change as we continue to move through the steps. One thing to note is that naming conventions can be different across the database. For example, patient is listed as all caps PT and T within allergies. However, within encounters is spelled out as patient. These discrepancies are common, especially amongst larger databases. Throughout the mastering process, we will uncover these relationships. Let's start with the data dictionary on the left. If you know the description, you can manually type it in. Otherwise, you can predict it. Clicking Predict will send the data to be compared with a dictionary of your choice. In this instance, we're using Wikidata. Wikidata is not always the most accurate because it does include extraneous information that may not be pertinent to your data. If you have an existing dictionary, you can choose to use that instead. One example would be FIBO, the Financial Industry Business Ontology, which is commonly used within the finance sector. Similarly, with logical names, you can choose to manually input them or predict them. Here are some of the results after comparing from Wikidata. After you've entered in all your descriptions, clicking Next will initiate a series of 4 comparisons that will assist in identifying matches in the data. Before each comparison, you will be asked which tables to select. Step number 3, the first comparison, is a direct column name. Going back to the example of patient, in the dataset, there were multiple tables that spelled out patient the exact same way. For each of the comparisons, the data steward can adjust the similarity or the acceptance threshold on the top to automatically accept or reject. The steward may also choose to manually accept or reject by clicking on the arrows to either the right or the left of the gray bar. In this instance, you'll notice that many of the tables have a column called AutoID that lists the unique identifier for all the rows in that table. Because all of these columns have the same name and consist of integers, the tool naturally thinks that they are the same column. However, the data steward would recognize that these are unique IDs for each table and that they should not be merged. Therefore, we will manually reject them by filtering for the ID columns and clicking on the arrow. If we click on the gray bar, we can see a sample of the data in both of the tables. Here we see that the values in the encounter patient and the claims patient tables are very similar. The check mark here indicates that the tool has already accepted it automatically since it reached the threshold. Since we're comfortable with the remainder of the columns, we'll move on to the next step, which is indirect column name matching. Again, we'll have to select which tables we would like to move forward. The fourth step, indirect column name matching, is similar to the previous step, except it does a fuzzy match between the column names. Going back to our patient example, we saw that in certain tables, patient was spelled differently. The layout here is similar to the previous step. If we adjust the threshold to be higher, you'll notice that the number of rows that are accepted automatically adjust. For the purposes of the demo, we'll assume that these are all accurate and move on to the next step. The fifth step looks at the semantic column names. Similar to how we predicted the definitions in step number 2, the tool takes the column names and sends them to Wikidata and compares the instances. The module will then link the columns with similar semantic meanings. Similar to the previous steps, the data steward would need to either accept or reject based on their knowledge of that data. The sixth step is the final step within the 4 comparison steps. This will look at high levels of overlap at the instance level through a subset of the data. It's important to note that these steps can be customized to do various matching routines. Some possible alternatives might include matching with a custom dictionary, as mentioned earlier, or exploring a database that has already been mastered. The last step reveals the mastered metamodel. Visualizations and analytics can now be run across the merged databases. This is the final metamodel, which has transformed quite a bit since the raw view from the very first step. The metamodel shows the connections between the table, and this image can be exported for further use.